Welcome to this explainer. Today, we're diving into a technological shift that honestly sounds a bit like science fiction. We are going to look at why ordinary table salt, yes, the exact same stuff you literally sprinkle on your fries, might just hold the key to the next massive revolution in global energy storage. I know it sounds crazy, but the chemistry is very real and it's scaling up as we speak. So, here's our roadmap for today. First, we'll unpack the lithium dilemma, then we'll peek inside a sodium-ion battery, break down the rocking chair principle, do a quick sodium versus lithium showdown, and finish up with the future of energy storage. All right, let's kick things off with Section 1, the lithium battery dilemma. Think about it. We currently rely on lithium-ion batteries to power our entire modern world, right? Everything from the smartphone in your pocket to the EV in your driveway. But extracting rare elements like lithium, cobalt, and nickel, well, that relies on incredibly costly, complex supply chains that carry a pretty heavy environmental footprint. This brings us to a fascinating question that energy engineers worldwide are desperately racing to answer. As our need for massive battery storage skyrockets, what if the foundation of our clean energy future was already just sitting right there in our oceans and on our dining tables? The answer to that question lies in sodium. And you've got to hear this metric because it is staggering. Sodium is over 1,000 times more abundant than lithium. To put that into perspective, sodium makes up a massive 2.6% of the Earth's crust, whereas lithium makes up a mere 0.0017%. Sodium is literally everywhere, and because it's not geographically limited to just a few countries, supply chain security is practically guaranteed. Moving right along to Section 2, inside the sodium-ion battery. So how exactly do we take this incredibly common element and turn it into a high-tech energy storage device? Well, looking at the primary components, these batteries make some really brilliant material swaps. They trade out rare metals for a sodium-based cathode, often using inexpensive stuff like iron and manganese. They use sodium salt electrolytes, but here is the real kicker. Pay close attention to the current collectors. Because sodium doesn't react with aluminum the way lithium does, manufacturers can actually use cheap, lightweight aluminum foil for both sides of the battery. That alone significantly drives down costs. Now, check out the anode structure. Unlike lithium, which nests perfectly into standard graphite, sodium ions are physically larger. We're talking about 1.02 angstroms compared to lithium's 0.76. And because they're bigger, they just can't slip into standard graphite easily. Instead, they need this disordered, porous structure known as hard carbon. It essentially acts like a microscopic sponge, creating this maze of nanopores that are perfectly sized to comfortably fit those larger sodium ions. Which brings us to Section 3. The rocking chair principle. Okay, so how do all these highly engineered components actually interact to store and release power on demand? Well, both sodium and lithium batteries operate on what's called the rocking chair principle. It's a brilliantly simple electrochemical mechanism. Basically, just imagine the ions as passengers on a microscopic ferry, constantly traveling back and forth between two shores, the cathode and the anode. The whole sequence is incredibly elegant. During step 1, the charging phase, energy from the wall forces the sodium ions to leave the cathode, swim through the liquid electrolyte, and embed themselves into the pores of that hard carbon anode we just talked about. Then, in step 2, discharging, the whole process just reverses. The ions rock back over to the cathode, and as they do, they push electrons through the external circuit. That flow of electrons, that's the actual electricity powering your device. And tracking the voltage curve reveals the really complex journey those sodium ions take as they settle into the hard carbon anode during charging. It isn't just a simple entry. First, the ions attach to defect sites in a phase called adsorption. Then they squeeze between the carbon layers, which is known as intercalation. And finally, as the battery hits full charge, they cluster together, filling up those deep nanopores. Honestly, understanding these distinct microscopic phases is exactly how engineers are tweaking and optimizing these batteries for better performance. Let's get to the fun part. Section 4, the sodium versus lithium showdown. Now that we've got a handle on the inner mechanics, let's put these two heavyweights head-to-head across a few critical metrics. Now, looking at energy density and cycle life, lithium-ion remains the undisputed champion. It definitely holds more power per pound and lasts through more charge cycles. But take a look at the bottom row. Sodium takes a huge lead by drastically lowering overall production costs, coming in at roughly $50 per kilowatt hour compared to lithium's $70. And if you want to know exactly why the production is so much cheaper, just look at this staggering financial contrast at the raw material level. The precursor material for sodium is vastly cheaper. We are talking about $60 per metric ton for sodium carbonate versus a whopping $6,600 for lithium carbonate. That difference fundamentally shifts the entire economics of battery manufacturing. But beyond just the cost, sodium-ion cells boast some incredible hidden advantages. Thanks to their unique electrolytes, they have exceptional cold weather performance. They retain about 90% of their capacity even at negative 40 degrees Celsius. That is a temperature where lithium batteries completely struggle to even function. Add in a far superior safety profile with a much lower fire risk and literally zero reliance on cobalt and nickel mining, you've got a deeply compelling technology on your hands. Finally, let's wrap up with Section 5, the future of energy storage. So, considering all this data, where does sodium actually fit into our rapidly changing energy transition? The reality is, sodium isn't necessarily here to kill lithium. If you're building a luxury EV or an ultra-thin smartphone where maximum range and minimum weight are everything, lithium is absolutely still your go-to. But for the heavy lifting of the green transition, sodium is perfectly positioned. It's totally ideal for massive stationary grid storage to hold solar and wind power, for affordable micromobility, and for heavy transport in extreme cold climates where a slightly larger battery just isn't a deal breaker. Which leaves us with a pretty compelling thought to end this explainer on. As the world attempts to scale renewable energy to unprecedented global levels, we are going to need more batteries than ever before in human history. Will the ultimate key to a stable electrical grid rely on fighting over scarce metals, or will it be driven by the humble, inexpensive elements found endlessly in ocean water and table salt? The chemistry is ready. The next few years will show us exactly how much salt the world is willing to use.